Hello, everybody. It's my great pleasure to welcome you to the EURADOS webinar, Radiological Consequences of the Attack with Nuclear Weapons. Paweł Olko will present the topic. My name is Agnieszka Szumska. I'm part of EURADOS and I will introduce our speaker and I will moderate today's webinar. Let me start with some information about EURADOS for those who are still unfamiliar with us. EURADOS is a non-profit organization for promoting research and development and European cooperation in the field of the dosimetry of ionizing radiation. The European Radiation Dosimetry Group comprises a self-sustainable network of more than 80 European institutions and about 700 scientists active in the field of radiation dosimetry. For this, EURADOS has established working groups in various dosimetric disciplines, such as harmonization of individual monitoring, environmental dosimetry, computational dosimetry, internal dosimetry, dosimetry for medical applications, retrospective dosimetry, and dosimetry in high-energy radiation fields. Contemporary EURADOS activities include intercomparisons, benchmark studies, scientific meetings, training activities, and annual meetings. You can get more information about the EURADOS and about our activities on the website, newsletter, and by following EURADOS social media like LinkedIn, Facebook, and YouTube channel. Feel free to contact us if you are interested in joining us and working together. EURADOS developed a strategic research agenda to identify the future research needs in the radiation dosimetry. This SRA was elaborated with input from EURADOS members and with the active participation of all the EURADOS working groups. The last SRA was published in 2020 as an EURADOS report, and which Paweł is also one of the co-authors. The new third version is under preparation. One of the best chances to gain EURADOS family and see exactly what we are doing is the next annual meeting, which will be organized in the middle of February 2026 in Helsinki. I just want to remind you that the deadline for the registration is the 30th of January and for early registration is the 22nd of December. So now it's my great pleasure to start with the webinar. The webinar will last approximately 1 hour and will consist of our speaker's presentation, followed by the discussion. The webinar is being recorded and as usual will be posted on the EURADOS YouTube channel and the presentation will be available on the EURADOS website. Your cameras and microphones are disabled. Questions can be asked in the chat. Francesco is moderating this section and at the end Paweł will answer the asked questions. Today's webinar topic is, as I mentioned at the beginning, radiological consequences of the attack with nuclear weapons. This presentation will be presented by Paweł Olko. Paweł works in the Department of Radiation Research and Proton Radiotherapy at the Institute of Nuclear Physics, Polish Academy of Science. Before he was Deputy Director for Research, he was the first director of the Cyclotron Center Bronowice, the only proton therapy center in Poland, and for many years headed the Department of Physics Application. He is a member of EURADOS Working Group 9, Dosimetry in Radiotherapy. He was also the EURADOS Vice Chair. He is a member of the Article 31 group of experts at the European Commission. He is commissioner of the International Commission of Radiation Measurements and Units, ICRU. His main research interests include microdosimetry, passive detector dosimetry, medical physics, radiation protection, and proton radiotherapy. He has published over 150 papers and scientific journals. So, Paweł, the floor is yours.
Good afternoon. Good afternoon, everybody. I will first try to share my screen. And no, 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 no. Okay, once again. Sorry for that. Mhm. Okay. As you learn from this introduction, I'm an expert in many areas. However, I'm not an expert in nuclear weapons. So how it happens that I decided to give you this presentation? It was the 2022. The Russian aggression in Ukraine started, and in that time, ICRP prepared a leaflet to advise for the members of the public on protection in case of nuclear detonation. And then I was asked by Werner Riem, could you translate it in Polish? So I did it. So when I did it in Polish, I started to read more about it. I got a lot of questions from people, and I look over the literature. And probably there is not many quantitative information. There are a lot of information about nuclear weapons, but not very much in which you can really find the hard data. The very big exception is the effects of nuclear weapons, compiled by Samuel Gladstone and Philip Dolan, and most of which is it is almost 50 years old, this publication. But most of my quantitative data from that are coming from that publication. Uh, Nowadays, nuclear war is back in the spotlight. Yeah, it's because of the repeated threats of the using nuclear weapons by Russian Federation, and also by testing new weapons like cruise missiles, like Poseidon torpedo, which is designed for destroying coastal cities, but also because there is really increasing public interest all over. I wonder if you had possibility to see the very impressive film Oppenheimer with Cillian Murphy, or to read the nuclear war scenario written by Annie Jacobson. If not, I really recommend it. The nuclear war was the topic also in the past. Yeah, there was the plans of nuclear war between NATO and Warsaw Pact, and this is the map pick up from the archives of the Warsaw Pact after 1990. You cannot see very well, but you see this red points, this red signs. Yeah, these are the places for the attack with nuclear weapons of the Warsaw Pact on the German and Benelux cities. And on the other side, there are black places. So there are the places where we expected that time the attack of the NATO nuclear bombs. So it was clear that the battlefield, which would take the territory of Germany and Poland, would be completely annihilated in case of the nuclear war. And that was one of the motivation that chief of staff of Polish army, so very high officer, Colonel Ryszard Kuklinski, delivered battle plans of the Warsaw Pact to NATO, and he was evacuated in 1981, and it was maybe one of the element which stopped to breaking the war in that time. So that is the outline of presentation. First, I will say something about the nuclear potential. So what are the current status of the nuclear potential in Europe, physics of nuclear explosion, health effects, which was really the title of my presentation. And at the end, I will present you some major points from the ICRP leaflet, advice for the public on protection in case of nuclear detonation. So that work which I was translating into the Polish. So at the moment there is some kind of balance between the Russian and American strategic nuclear potential. Both sides have about 2,000 of warheads, which are the warheads in some launchers on the ground, but also in submarines. But there is a big disbalance as far as the tactical warheads. So tactical, that means the warheads which could be used not only in the battlefield, but also for short distances up to 1,000 kilometers. So here, NATO has very limited potential, including United States, France, the United Kingdom, and for example, Russia and Kaliningrad. They have, with the range of about 1,000 up to 2,000, 5,000 kilometers, they are able to reach all major points in Europe. Oops, sorry, but it's oops. Okay, so what was the situation in Ukraine? Up to 1994, Ukraine was the third nuclear superpower in the world, with about 2,400 tactical warheads and 1,200 strategic warheads. So altogether, almost more than 3,500 strategic warheads. And they had also very well developed industry, producing rockets, airplanes. Up to now, part of this industrial complex were located also in Donbass. And if somebody visited Ukraine, there are some museums located in the places of the former bases for the intercontinental missiles. One can visit really the places where they were the rockets, intercontinental rockets, were prepared to be launched. And that's what's happened in 1994. In January 94, the presidents of United States, Russia, and Ukraine, Bill Clinton, Boris Yeltsin, and Leonid Kuchma, signed in Moscow the declaration to eliminate Ukrainian nuclear weapons. And in December 5th, at the Budapest, they provided security guarantees to Ukraine. So what was written in these guarantees? It was memorandum of security assurance. So Russian Federation, United Kingdom, and United States reaffirmed their commitment to respect the independence and sovereignty and the existing borders of Ukraine, and their obligation, they obliged to refrain from threat or use force against the territorial integrity. And it was signed by Boris Yeltsin, Bill Clinton, and John Mayer. In April 2023, in an interview with the Irish broadcaster, Bill Clinton expressed regret at pressuring Ukraine to give up nuclear weapons. It's of course, it's very, yeah, I cannot find good words to say about this. Yeah, and we can always we can compare. You see the number of deaths in Ukraine, which is approaching about 1 million people, with the offers of the Hiroshima and Nagasaki, with about 140,000 people. So that was the price for signing this treaty. Okay, now how the nuclear bomb is working. It's based on two physical principles, on fusion and fission. This figure here is one of the most important figures in the nuclear physics. It shows the average binding energy per nucleon versus the number of nucleons in nucleus. When we start the fission, so when two light elements are connected in the reaction, and the heavier element is produced, a huge number of energy is released. And also we can go in the other side. The fission of heavy nucleus like uranium 235 leads to production of the elements, which in total the average binding energy per nuclear is higher. So since also in this type of reaction more than one neutron is produced, the chain reaction is possible. And it was very fast identified. Already in the discovery of fission, it was 1938, and in 1939 the Hungarian physicist Szilard, he together with Einstein, they wrote the letter to President of the United States, to Roosevelt, to inform him, to warn him about the possibilities of producing these destructive weapons, and to asking the president to start research in this direction. So The chain reaction is possible when the certain amount of fission material is available. It is called so-called critical mass. If the mass is too small, more neutrons are escaping the volume. But if the ratio of the range of these neutrons to the size of the volume is increasing, then the chain reaction is possible. The sustainable chain reaction is possible. One can increase also this effect by introducing neutron reflector. So how many material do we need to build nuclear weapon? There are different nuclides which we consider which are useful for that. Uranium-235 with a very long half-life, critical mass of 50 kilogram and diameter 17 centimeter. But for plutonium, we need only 10 kilogram and about 10 centimeter in diameter, which can very well fit, for example, to the artillery bullets. What is the mechanism of the nuclear and thermonuclear explosion? So the plutonium, the fission material like plutonium or uranium-235 is put in such a way that after the explosion of the of so-called high explosive lenses, the critical mass is produced, and the fission, the chain reaction happens. Then explosion creates a hot plasma that compresses the fuel and ignite a fusion reaction. What is interesting is around the uranium-235 and plutonium, there is so-called tamper, the uranium-238 tamper, and this tamper is first is the reflector of the neutrons, and the second can give this the possibility to suppress the pressure at the first moment, so it increases the power of the explosion. This same uranium-238 tamper is used also in thermonuclear reaction. What are the main damaging factors for the nuclear explosion? In this figure, we see that the main energy which is transmitted during the nuclear explosion in fission, it's a blast, it's a shock wave. So about 50% of that, about 35% is a thermal radiation in form of heat, and only about 15% is delivered in form of the nuclear radiation. First is the prompt nuclear radiation, also as a radioactive fallout. However, it is possible to enhance the radiation efficiency in this type of weapons. In case when we remove this uranium-239 tamper, then the power of the explosion is higher. However, the radiation which is produced, the initial radiation which is produced, for example, also including the neutrons, are not moderate. So then we can in such a case to get about 45% of the energy could be emitted as a prompt radiation. And these enhanced radiation weapons called neutron bombs were planned to be used against especially against the Warsaw Pact tanks, because the Warsaw Pact had many advantage in the number of tanks, and the goal of using this enhanced radiation weapon was to eliminate just the tank crew with a very, very high radiation dose given within a very short time. But this weapons was eliminated from the NATO arsenal after the end of the Cold War. It is interesting to ask what is the radiation spectrum which is emitted during the nuclear explosion. What you see here, you know from this figure, you know from the school. It is the Planck radiation law, which says that black body, when in the given temperature on few thousand kelvins, is produced electromagnetic radiation, and length of this radiation, so energy of the radiation depends on the temperature. So energy of the emitted radiation increases with the temperature. However, when we have atomic weapon during the explosion, the temperature goes up to about between 10 million and 100 million kelvins. So when we look for this figure, here we have the photon energy. Here it is 1, 10, 100, and 1 keV and 1 MeV, and that is the let's say the spectra, radiation spectra produced due to the Planck radiation law. So we see that the spectrum emitted is depends on, of course, on the type of explosion, but it contains a lot of X-rays. X-rays produced just from using this principle. On the left-hand side, we see the radiation spectra, gamma ray radiation spectra, calculated for Hiroshima and Nagasaki bombs at the given distances from the times of explosion. We see still a high contribution of X-rays, of low energy X-rays, and lower contribution of the high energy X-rays. However, when we look at the right-hand side, when here we have the mid-value energy beams, and here we have the kerma to tissue, we see that the prompt radiation, which is emitted just during the explosion, has higher energies. It's produced by higher energies, and the low energy, so the delayed radiation, is produced with lower energy. What is prompt? What is delayed? Prompt is that what happened during the initial second when the explosion take place, but because of the tamper, because of this uranium 238 tamper, it is greatly reduced. So most of the emission of the gamma radiation happens from the growing blast, which growing cloud, radiation cloud, in the first minute after the explosion. So prompt gamma radiation itself is absorbed mostly in the bomb, and it's only about 1% of that what is emitted in the first minute, but the emission is prolonged to several seconds. And here is the first picture from Glaston and Dolan, which shows what is the percentage of dose, initial gamma dose received in the function of time. So we see that about 2 seconds after explosion of the thermonuclear bomb, only about 20% of the total dose is emitted. After 5 seconds, it's about 50%. So in principle, there is still some time to hide under the cover to decrease the absorbed dose. And there are what are the absolute numbers for the doses versus the range, the distance from the explosion. We have two different warheads, fission warheads and fusion, and I just put on red the value of free grays, which is considered to be the lethal dose, and for the Hiroshima and Nagasaki bombs of about 20 kilotons, the distances of about 1,700 meters. So yards, so it is about 1,500 meters, and similar is for the fusion. When we take 1 megaton bomb, the free rays of gamma rays is received from about 3,000 yards, so it is less than 2,800 meters. Similar situations for neutrons. And for neutrons, the numbers are 1,500 yards, and here it's about 2,500 yards. So at the distances of the lethal doses from prompt radiation are received after in the distances of about 3,000 meters after the explosions of fission or fusion bombs. Please note that the neutron doses are given in grays, not in sieverts, because of course the WR which we are using in radiation protection is valid only for stochastic effect and not for the prompt effects after acute irradiation. Of course, those can be reduced when we are in the shelter, when we are in sometimes behind the various structures, and being in the basement can change or reduce the dose delivered by the X-rays by the factor of 10, and similarly is neutrons. In shelter, which is covered with earth, with 1 meter of earth, the reduction is by the factor of about 100, is up to 100. So we see that sheltering and being inside, behind an material heavy in the building, it can reduce significantly the dose by factor of 10, up to from 10 to about 100. So when the war in Ukraine started, the commercial activities of any building companies really increased, and they are now, it is possible to build in your garden own shelter, and you see the price of such an independent shelter, which is equipped in concrete doors, in ventilation system, second exit, additional stairs. It's about between 100 and 200,000 euro. What are the other damaging factors of nuclear attack? As I mentioned, the most destructive is blast and the shock wave. This figure shows here the effect of the nuclear explosion in air, and shows the time of arrival of the blast. So after explosion, the distance of about 3,000, 4,000, 5,000 meters is achieved after several seconds. So the shock wave arrives at 5 kilometers at about 12 seconds. What is the destruction? What is the destruction using the let's say shock wave? When it is considered that the pressure of 5 pounds per inch, which is about 0.35 kilograms per centimeter square, it produces a total destruction of the buildings, because per 1 square meter we have the pressure, we have the force of about 3.5 tons. So it leads to the total destruction. But if we look for the range of such a shock wave, so about 5 pounds per inch, we are getting at the distance of about 5 kilometers when after the air blast explosion of the relatively large nuclear warhead of 800 kilotons. So 5 kilometers destruction due to shock wave. If we look at the thermal attack of the thermal blast, so the third grade burns will be, for somebody who is outside, it is not hidden, it's on the radius of about 11 kilometers. So it's really significant, yeah. And such a thermal flash causes not only injuring of the people, but also the firestorms, and the firestorms are probably the most destructive. The firestorms, like it was, for example, produced in February 45 in Dresden, where the firestorms were very destructive for the people, even in the shelters. And now, when we compare this with the range of the ionizing radiation of the exposure, so we see that the radius of the radiation where causes the lethal doses is much lower than the radiuses for the shock wave or for the thermal heat. Yeah. So looking here, it is quite clear that at distances where exposure leads to lethal doses, shock wave and thermal radiation are the main risk factor. So if we survive the shockwave, if you survive the burns, so if you are somewhere in the shelter, probability that we will be mostly affected by the radiation or the prompt radiation is very low. Of course, we were talking about the prompt radiation, but the second sometimes even more dangerous effect of radiation exposure comes from radioactive fallout. A radioactive fallout depends on the height of explosion. If the explosion take place in air, very high in the air, then there's practically no fallout. If it is in the middle altitudes, 500 meters, it was just the altitude in Hiroshima. Then here it is shown one example again, 800 kiloton warhead, and after some hour we have some 35-kilometer long pass with a dose rate, significant dose rate of 1 sievert per hour, and some. But if the same explosion takes place on the ground, then the explosion activates material on the ground, leading to really significant radioactive fallout, which consists primarily of the short-lived beta isotopes. And then, of course, the area which is covered by such a high dose rate fallout is really significant. It's really hundreds of kilometers, could be up to hundreds of kilometers. The good message here is that the dose rate from this fallout decreases very fast. So after the explosion, the fallout, it depends, of course, on the atmospheric conditions, but after the explosion, you have some up to 1 hour to hide. And if we look what's happened after 24 hours, here we have on the x-axis, we have the time after explosion. Here we have 1 day, and after 1 day, the dose rate decreases by the factor of 500. And after 1 week, the dose rate decreases by the factor of about 5,000. So it goes very fast. The fallout is mainly built, so it consists from short-living beta isotopes. So when you hide, when you are in the shelter, you have a good chance to survive it. And this is some information from the Radiation Emergency Medical Management of U.S. Department of Health and Human Service, which is giving some hints what to do during the contamination. And they say that more dangerous is a hazard from external exposure during the fallout, and not contamination, which is less, let's say, less immediate life-threatening. So never delay urgent medical treatment due to contamination concern, and shelter should never be denied due to the contamination concern. So first of all, you have to decrease your external dose rate, and of course, if you can make yourself the contamination, but it is not so essential like being protected for gamma rays, for penetrating gamma rays. So what is the health effect? What are the health effects after the exposure? This is the figure adopted from Gonzalez from very nice Sievert lecture some years ago. And we have stochastic and deterministic effect, and the deterministic start from about maybe half a sievert, and below the stochastic effect we see only the epidemiological effect of radiation action. And when we talk about the acute irradiation, which can happen during the explosion, about 50% of people dies in 60 days after doses of about 3 grays. It is in particular by limited medical support, but of course, in case of such an attack, we cannot count on some very very sophisticated medical support. So these are the numbers which are But also if we are irradiated over 1 week, so if we talk about the radiation fallout, then the 4 to 8 grays of protracted radiation can lead to the fatal results. It can lead to the death. Of course, there are also some other effects like skin burn, like permanent sterility, like increased risk of circulatory disease. But in principle, what is the most important is to survive the attack. So 4 to 8 grays protracted over 1 week. These are the data from ICRP 146. So the question is, can we make the dose assessment after the explosion? And of course, after that, we have developed many methods of accidental dosimetry, also some supplementary methods. And there is a very nice ICRP report, also written by our EURADOS colleague, the co-authors of this report. But after large-scale attack, such a assessment of absorbed dose in a big population is fairly impossible because of the scale of the damage. And probably one of the easiest methods to know the prognosis of people irradiated during the explosion is the control of the lymphocyte number of lymphocytes. In the irradiated people, the number of lymphocytes decreasing very quick, and such a number, so the lymphocyte count can be done under very simple light microscope. So even if the sophisticated machinery in hospitals are not working, that can be done by microscope. So that is one of the possibilities to assess possible risk for the high injury of using the radiation. So what is the effect of exposure for the lower doses? We know it from the population of Hiroshima and Nagasaki, where about 120,000 people were studied, and most of those people received a relatively low dose, so below 100 millisievert, about 14%, and was up to 500 millisievert, and only a few percent, because those probably did not survive the explosion, were exposed to higher doses. And the effect of mortality, 47 years of observation, there was about 440 deaths were attributed to radiation exposure, and the resulting risk factor after was assessed is about 1% for leukemia, about 11% for acute exposure. But if we take into account the prolonged exposure for dose and dose rate effective factor, it is of about 5% for 1,000 millisievert. When we talk about damages to the genetic material in reproductive cells, the data from Hiroshima and Nagasaki are not giving the right answer, so the conclusive answer. And this risk of hereditary effects after exposure of parents of about 0.4% on 1 sievert was assessed mainly on the studies of the animals. But the natural background of the genetic changes in human population is similar. So very high exposure doesn't lead to significant increase of risk of hereditary effects. The most significant effect is the exposure of the fetus so the prenatal exposure. The exposure of fetus leads to increasing risk of mental retardation and lower intelligence quotient. It is particularly important for the fetus between 8 and 15 weeks of pregnancy. And but these effects were observed only for doses exceeding 0.2 sievert, so relatively high doses. As far as childhood cancer incidence following parental exposure, no association was found between the parental gonadal exposure and an increased risk of childhood cancer or other types of death. So that was the good message. So in summary, we have some for deterministic effects are observed in principle above one sievert. Stochastic effects were observed for doses exceeding zero point 0.2 sieverts, and the most significant effects could be observed for the prenatal exposure. Yeah? However, the risk associated with exposure to ionizing radiation is much lower than those associated with exposure to blast and to thermal radiation. In other words, when you survive the blast and you survive the shock wave, you have a very good chance to survive. So that's the message, because the radius of the action of the blast and the thermal is much higher than the lethal radius of radiation exposure. At the end, I would like to give you to report you or to show you some elements of this ICRP leaflet, advice for the public on protection in case of the nuclear detonation. So first of all, go inside and stay inside. So get inside the center of the building or basement to put as much material between you and radioactive material outside. So how to be prepared for the nuclear detonation? Identify potential shelters, agree with your family and friends about your action. And what is interesting, or maybe not everybody can remember about such things, add name tags to close or small children, because if they are somehow lost and so on, it will be possible then to find them, to identify. And of course, prepare and store some backpack with some first aid and water and spare clothes and things like that. So the first 10 minutes, the best way to protect you and your family after a blast is getting inside the center of the building. Be inside before the fallout arrives. The fallout could be really much more destructive, especially if you are far away from the explosion. What to do in the first 24 hours? So contaminated clothes and footwear should be removed if possible, but food and drink medicine which you already have is safe to be consumed. Tune to any available media, such as AM stations. Probably the FM station will not work, because AM stations give you the range of several hundred kilometers, and that will be probably the only possible communication method. Remain in the most protective location for the first 12 to 24 hours. Remember that 24 hours decreases the fallout dose rate by the factor of about 500. And of course, in that time, self-evacuation is strongly discouraged. So, in summary, the nuclear attack brings a devastating destruction due to the blast and thermal radiation, but the area of the high lethal radiation doses are well within this area, and so sheltering during and some days after the attack leads to significant reduction of absorbed doses, and sheltering will mostly prevent clinical effects and significantly reduce the stochastic effects. And at the end, let's say one of my own conclusion is, I don't believe that nuclear weapon will be anymore used in the war, because the equibalence between the superpowers makes the nuclear war not effective. The nuclear weapons are most effective if they are not used. Thank you very much for your attention.
Thank you, Paweł, for your nice presentation. And now we have time for questions. A few have been asked in the chat. So, Francesco, please ask the questions for our presenter.
Yes, so we have at least 5 questions. The first one comes from Alexis Papadopoulos. Professor, I wanted to ask you whether it's meaningful to study the radiation RBE quality factor Q after an episode of a nuclear weapon, given the fact that the dose uncertainties and the dose levels are too high to be concerned in both cases.
For the acute, as far as I learned, from the, let's say, studying this literature, which is available, for the acute irradiation, the Q is not important. So the really absorbed dose is important. For long term, that we have the Q or the radiation weighting factors from which were learned from Hiroshima and Nagasaki. In particular, because there were two different bombs. One was uranium and second was plutonium. There was somewhat different neutral spectra. That was one of the elements to find out or to establish the value of the QR. But for the acute irradiation, dose and not dose equivalent or others is important.
Thank you. Then we have some questions that are more like to be comments than questions. So please, if I did not understand well, write it again in the chat, but they look like comments. Another question comes from Johnny L. Fegali. My question is, before creating atomic bombs, did any of these governments consider whether we have the power to limit their danger and protect people in case of accidents? Is there advanced radiation protection policy or any ideas that could protect and cover populations before and after accidents, or simply evacuate them to another planet?
Okay. As I said, I don't believe that nuclear weapons will be now used because too many parties for too many parties the nuclear weapons is available, and as we learned already in the peace in Europe in the last 70 years was maintained because there was some balance between the East and West, and both sides had enough nuclear weapon to destroy the other side, yeah. And that was they gave us the guarantee of peace. Ukraine stopped, delivered, so resigned from nuclear weapons and paid a very high price for that, of 100,000 of people, and also from Russian side. It is a big tragedy. Probably if they own the nuclear weapons, there would be no such a war, yeah. At least this is that's what I think, looking at the history and that what is going now within the world.
One of the participants also answered, weapon is to kill people, not to protect them. And then there is another question coming from Václav Matejka. Which radionuclides dominate early dose contributions in the first 24 hours after a nuclear detonation?
Very good question. I was looking the literature and I didn't find really the good question. Why it is difficult to say, because it very much depends on the height of the attitude at which the explosion takes part, and also on what type of ground it is, in the water or in a different ground. So I didn't really. I look hard for that spectrum, but I didn't find. I found the X-ray spectrum. I didn't find the beta rays. Okay, what are after the explosion? Yeah, sorry for that.
And then, which I think is the last questions, comes from, don't know how to pronounce the name, sorry, Chetan R. Gupta. The question is, having said that most of the countries have already started the uranium enrichment for green and clean energy source, monitoring and supervising is not possible at the site. How this could be overcome? Maybe by the agency, any other agency or organization doing the same job as the agency?
Yeah, IAEA is doing the job since 1967. In 1967, three superpowers, it was the Soviet Union, United States of America, and United Kingdom. They signed they proposed the Treaty of Non-Proliferation of the Nuclear Weapons. And then for the Eastern Bloc, the Soviet Union, let's say, controlled the East Bloc countries that they are not developing all nuclear weapons. And practically from that also time, no one NATO partner made his own nuclear weapon. Why? Because it was all the countries were signed the treaty, and then they were controlled by the IAEA. Of course, there are some examples. We know all the examples all over the world. The people are anyway using or producing the fission material, the enriched fusion material. But okay, that's some political decisions. Yeah.
Then we have a question coming from Michael Hay. Let's talk about EMP. How must radios be prepared to survive an EMP?
I think that's the completely different talk. Yeah, the electromagnetic pulse is produced when the explosion takes place in the high altitudes, and so let's say 30 kilometers or 100 kilometers, and then it works like that there's a lot of Compton electrons are produced, and after the explosion, and it produce a very strong electromagnetic pulse, which is dangerous for the all type of electronics. There are some time also in which this electromagnetic pulse is effective. Okay, but this is the separate. Yeah, it's really dangerous for the electronics. We are all based on the. All our life is now based on electronics and the electricity. But okay, I cannot answer how to be prepared. That's I cannot answer really professionally.
Okay, thank you. In the meantime, a lot of participants are writing on the chat, answering some questions. For example, Thomas Peltonen put a link to answer the question of which radionuclides are there. Thank you very much, Thomas. Johnny Elfegali answered to the agencies. There is the Vienna Center for Disarmament and Non-Proliferation. Liz Ansbury answered the question for the radionuclides with a link to the project Pianoforte. So participants are also answering. There is another question for you. Do you think that, coming from Alexis Papadopoulos, do you think that microdosimetry would be adequate for dosimetry and radiation quality measurements, or more average quantities should be used for this purpose of massive radiation?
Microdosimetry was created, you see, to understand the action of the low doses. So practically, that is the origin of microdosimetry, and also to understand the neutrons. Yeah, it was the middle of 50s. The neutrons appeared as a problem also in the nuclear weapons, and so radiation actually was studied. Microdosimetry gives you some answers for when you deal with irradiation of the small biological targets, and the bigger difference is when you have low doses and some of the targets are affected and some of them not. Yeah, and now it's the question: what is the probability that these affected targets will lead to some effects, for example, at the end to the cancer? You see, so this thinking in terms of microdosimetry leads a little bit to the linear non-threshold hypothesis, because it says, okay, even going to very low doses, we can have the cells which are exposed to high doses, to the high Z events. But in fact, the biology is much more complicated, and some low doses, for low doses, in fact, we don't see an effect. So from one side, yeah, microdosimetry to understand the energy deposition is useful, but on the other hand, there are not many effects which could be really significant for the low dose exposure. Microdosimetry is also to understand the let's say high LET exposure, so the difference between, for example, which is important for radiation therapy, but then, okay, that is another cup of tea, a little bit.
Okay, thank you, Pavel. There are no questions anymore. Please, I ask participants to write something if I missed some question, but I don't think so.
Okay, so we are perfectly in time. So thank you for your participation and for a lot of questions and remarks. Thank you, Pavel, for nice presentation. We have a lot of questions, so it looks it was interesting topic. I would like to end now and just summarize, like Pavel told, that hope that nuclear weapons will be never used. So thank you for your attention again, and please follow our social media and subscribe our newsletter to see all our activities.
Thank you a lot to everybody for the attendance. It was a pleasure to be here. Thank you.